Hi everybody, welcome back. This is lecture 2 of quantum information. Today we'll talk about the structure of quantum states, quantum transformations, and quantum measurements. So let's start with states. So you've already taken some quantum mechanics and you're familiar with that quantum states look something like this. This is the Dirac-Braket notation. But I'm going to try to simplify this quantity as much as possible. So this bra, or the ket is nothing more than a column vector. So let's call it S1, S2, ... And then the corresponding bra is nothing more than a row vector, but the entries are conjugated. So going between these two, we have to transpose. Transpose simply means turning a column into a row, and conjugate. And conjugate simply means taking a plus ib into a minus ib. Okay, so a quantum state is just a vector. Now, probably the types of quantum states that you've dealt with, for instance, of harmonic oscillator or the infinite well, where you have a position degree of freedom, this vector is infinite dimensional. And infinities are tricky. Infinities bring all sorts of complications that have to be dealt with subtly. So for instance, you have to deal with things like the Dirac delta function, and integrability of these infinite dimensional vectors is still to some extent an open topic in the mathematical physics community. Now, the good news is that we won't have to deal with any of that. We're going to have to deal with only finite dimensional vectors. And this is because, remember our bit. Our bit was represented by, so we have our bit was either a 0 or a 1. And a 0 we wrote as a vector like this, and 1 we wrote as a vector like this. And so, and then we can also generalize this, so we can write a vector like this, and we define this idea of tensor product. So this is a 3-bit vector, sorry, a 3-bit state, which we can write as in vector notation like this, and we can go through and carry out the tensor product like this. And this is the state of 3 bits in the vector notation. So we're going to generalize this and for quantum mechanics. So the generalization of a bit to quantum mechanics is, as you might imagine, is a qubit. Let's change the color. So I'll talk about the state of a qubit. So a qubit is very much like a bit. We have two possible states. Qubit can be in state 0, which we can write like this. So somehow the pen stopped working for a second. Qubit could be in state 1, which could be written as like this. And then the departure from the normal bit starts here. And this is where we allow for things like quantum superposition. So a generic state of a qubit we'll write as a psi is equal to some number alpha times 0 plus beta times 1. Okay. With the restriction, and this is the restriction that quantum states have, that alpha square plus beta square is equal to 1. Ooh, this paper is acting up. Let me go to a new paper. So, qubit. So again, a qubit can be in state 0 or state 1. There's something special about these 0 and 1, which we often call computational basis. Or Z basis. And you'll see why at a later point. But a generic state of a qubit, psi alpha 0 plus beta 1, can be written as alpha square, it has to satisfy the condition alpha square plus beta square is equal to 1. And we'll see why that is in a minute. So a bit can only take two possible values. Bit can take the values that the qubit can have in the computational basis. It can be in state 0 or it can be in state 1. But qubit can be in an arbitrary superposition of these two basis states. And a priori, it's not obvious that this means some huge advantage. This means that quantum computation is going to be better than classical computation. But we will see that in fact, we will see at some point in this semester that in fact it does allow us to do something more interesting. Often we will write psi, a single qubit state, as cosine of theta over 2, 0 plus e to the I phi sine of theta over 2, 1. It's a trigonometric parameterization. And by the way, I should say that I'm now following the book, so you can also follow the book for this. And the book has this nice picture which I'm going to try to mimic, which I won't probably be able to do. And so you draw the Cartesian coordinate and you draw a sphere around the Cartesian coordinate. So this is my x-axis, y-axis, and z-axis. And the generic state of qubit is a vector on that sphere. This is a unit sphere where this angle is theta. Now this thing has a projection onto the xy plane, and this angle is phi. And this right here is state 0. And this is why it's called the Z basis. And if we take the bottom point on that same axis, I'm not going to try to draw it, that's going to be state 1. So those are the bit states, 0 and 1, along the Z axis. But qubit can take any state on that sphere. Now, that's already something quite interesting, and we'll come back to that. No. Oops, I think I know what's happening. There we go. Okay, so we're back to the page. Sorry, just making a note here. Okay, so I'd like to take a slightly divergent approach for the second. So previously I argued that the state of a computer, or the information state, is more general than physics. And I'd like to expand on that at this stage. So let's go back to the classical state. So a classical state, which is just a state in terms of bits, we'll write that as an X. How is this more general than a physical state? Well, this state with bits, I can write down state of any physical system, right? So that's already amazing. And then I can define computational functions that allow me to go from any one state to any other state. And we talked a little bit about functions last time. So if this is a physical state, and if this is a physical transformation, then by definition this will also be a physical state. In other words, I can do physics on a computer. And in fact, a computer can in fact simulate any type of physics. And this is why we can run all sorts of simulations on Mathematica or some ray diagram program or MATLAB, etc. So the amount of information, the size of the information state determines the complexity of the physical system. So in other words, if we talk about the size of X, that is some notion for how big the physical system is. This is somehow size of system. And by absolute value around X, I mean the number of bits in X. And then we can write down F as a set of gates, F1 to Fn. So we can think of it some elementary set of gates, and we'll talk about that in a few minutes' time. And the number of gates that are required to make this physical transformation. So N is the complexity of the dynamics of the transformation. And so there are two takeaway messages. One is that the information state and information transformations contains all physics as a limiting case. And physics is more interesting because it's limiting, because you can't do everything. And that's where this idea of physics intuition comes from. Not all mathematics is going to be relevant. The second takeaway message is that by understanding the size of the system and the complexity of the transformation, we can say something about the complexity of the physical system. And to give you an idea, suppose you want to simulate a pendulum. Now, pendulum is a fairly simple system. It's a differential equation which you can even approximate for small angles, and you can write down the solution for pendulum and its period relatively quickly. It's something we do in first year physics. But suppose you want to simulate a double pendulum. Now this is a far more complicated system. You can also write down a differential equation for this, and you can also simulate this, but the number of parameters involved in the second example will be a lot higher. And if you try to go and write a program on Mathematica, you'll very quickly discover that, in fact, a double pendulum is a far more complicated system than a single pendulum. And the other way to think about that is just go look at the motions that a double pendulum allows in comparison to a single pendulum. Okay, so I want to come back to the bit, qubit. So since I can write down any state of a can write down qubit in this terms of two real parameters, theta and phi. Then can I take theta to be arbitrarily complicated? So I can take theta to be 0.12311. I can take an arbitrarily long real number. In fact, I can take all of Shakespeare's plays and I can encode them into this number. So the collected works of Shakespeare can be added to this single number theta. And this already shows us that a single bit can carry a huge amount of information, but that's not the advantage. So if we were to do the same thing for bits, so size of the bits would be equal to the number of letters in the collected works of Shakespeare. So we're not going to get an advantage. We're not. So if we think about how many bits it would take to write to store collected works of Shakespeare, it would be roughly equal to the number of letters times some multiplicative factor, which I'm all worried about. But I can, in principle, do exactly the same thing for with a qubit, but I can do it in a single qubit. So somehow a single qubit seems far more powerful. And it's too good to be true. So we'll see why it's not true in a few minutes. I'm looking for my next page. Okay, transformations. So in quantum mechanics, a transformation is something that takes one state into another state. Now remember, in classical mechanics, we had ideas like energy conservation, momentum conservation. We're going to have the same types of constraints here. So quantum mechanics still respects energy conservation and momentum conservation. There's no issue with that. So let's say that this state we write as alpha and beta, which is the same as alpha 0 plus beta 1. And like this state is, say, delta and gamma. So it can be written as delta 0 plus gamma 1. So now we need some rules on how these transformations work. So one possible rule is that we might want to be able to go back to the original state. If that's the case, then we need this transformation to be reversible. We also want to make sure that we have the rule here that alpha squared plus beta squared is equal to 1. We also want to make sure that the output state has the same rule. Now, so if we want to preserve normalization plus reversibility, then we wind up with transformations that are, these two give us transformations that are unitary. So U acting on psi, which is our first state, gives us phi, which is our final state. And a transformation is unitary if, well, first of all, let's discuss what this transformation looks like. Well, if this thing is a vector like this, and this thing is a vector like this, then the unitary is just a matrix. Let's write it as A, B, C, D. And if we multiply the matrix out, then we get A alpha plus B beta plus C alpha and B beta is equal to delta gamma. Turn off that camera since it keeps getting in the way. So a unitary transformation or a transformation is just a matrix, and unitarity, and I won't prove this, but we'll discuss this here, so properties of unitarity are that U times U dagger is equal to the identity matrix. So the identity matrix is just the special matrix like this, and U dagger is same as U, but transpose and conjugate it. So A, C, B, and D, where every one of these numbers is conjugated, and we've moved B and C around. So first we've done a transpose, and then conjugation. Actually, it doesn't matter whether you conjugate first and transpose second or the other way around. Okay, so pictorially what it's doing, if we go back to our Bloch sphere, remember our state psi was some point on the Bloch sphere. All the unitary is doing is rotating this initial state into some other state. So a unitary transformation is just a rotation in the Bloch sphere. So this sphere is called Bloch sphere, which is a funny name if you think about it, but it's named after a person, Bloch sphere, not supposed to represent a block. So B-L-O-C-H. Okay, so those are our unitaries. Now we're gonna put the unitaries and states together to talk about what a quantum computer is or what a quantum processor is. So first thing is that we started with a single qubit. And single qubit was alpha 0 plus beta 1. So what if we have two qubits? Well, it's not all that different from having 2 bits. We can write 2 qubit states as, let's use different letters, A 0 0 plus B 0 1 plus C 1 0 plus D 1 1. In general, we can define a basis state for n qubits so the basis is something like 0 0 0, all zeros. We'll start with A plus B, whereas all zeros except for the last one, and so on, and then C times 1 0, and we can write down, so this is a 0, so we can write down a n qubit state in terms of these bases, computational bases. So all a computational basis is for n qubits is a set of binary numbers is the set of all binary numbers written in terms of kets. And a generic state, so let me call this let me call them in terms of let's label them into something more compact. We'll call them little b sub k, and I can write down a generic n-qubit state as some coefficients alpha k with computational basis elements vectors beta k. Now we still have the fact that alpha k squares sum over k is equal to 1. This is exactly the same as previously alpha square plus beta square equals to 1. Okay. Now the thing about computational basis or any other basis is that basis in Hilbert space is orthonormal, so we have things like bk, bj is delta kj. Also, we have the completeness relationship ek, bk, sum over k is just an identity. Okay, so that's a complete orthonormal basis. Complete meaning it includes the whole space. That's what it means to be identity. It has support on every part of the space. Okay. So now suppose we start with some generic state like say 0, 0, 0, a few qubits. How do we turn that into some more complicated state, psi, which is equal to alpha k bk, where these are the basis states? Well, we apply a transformation, and that transformation would be unitary. Now, that unitary in this case would be acting on 5 qubits. But what we want to do is we want to be able to come up with ways of applying this unitary in some more realistic way. So we don't want to have to come up with physical mechanisms for interacting all 5 qubits. Now, there is a little bit of dogma that we have to appreciate, and part of it is that 5 qubits or 5 bodies tend not to interact with each other in the real physical world. It just happens to be that way. So what you normally have is you have 2-body interactions, sometimes 3-body interactions. And this dogma is also true in computer science. And you can think about it this way, that if you're doing a computation and you have a bunch of transistors that are doing some calculation together, it's very difficult to interact a transistor over here. Let's say these are my 10 transistors, transistor over here on my pinky on the left hand to a transistor over here, pinky on the right hand side. So instead what you do is you come up with a smaller set of unitaries and you try to construct this big generic unitary that you want. And the way you do that is that, well, let's draw 5 lines. So what I'm going to draw here is a quantum circuit. So this is the initial state. My time is going this way. And now I'm going to apply different gates, these different colors. And these gates can be applied to 2 qubits. Okay. Or the gates can also apply to single qubits. Or sometimes there are no gates being applied. And after we apply a bunch of these gates, our goal is to prepare here. Oops. Let's go back to the original color. Is prepare here state psi. In other words, this circuit, you can think of it as starting with a bunch of zeros. The circuit is simulating some big unitary U for us. So these things, these gates, are also unitaries. They're little u's, let's call them. So let's call this U2, U1, and we have a finite set of gates. So U1, U2, U3. We have some finite number of gates, U1, U2, and U3. And by putting them together, some combination of them, I'll write it as that, can approximately give us any big unitary, any unitary on n qubits, or let me put a D here for depth. So I've applied for some number of layers. So these are the layers that I'm talking about. So applied them D times, and that approximates an arbitrary unitary. And here, let's make this a bit weaker. We can make it an approximate. It doesn't have to be perfect. So on the right-hand side, we have a generic physical quantum process that we want to simulate. And on the left-hand side, we have a algorithmic way of simulating that quantum process with a finite set of gates. Some predetermined set of gates. Excuse me. Now this right here is the essence of quantum computing. Well, I should say this is the essence of computing altogether. Classical computing is contained in this. So classical computing is a subset of quantum computing. How do we see that? Well, remember, these were just bits. So qubits contain bits, right? So if I just start with state zeros, and all classical computing is, and I'm going to do this without proof, you can do any classical computing with a gate called NAND, which turns out to be a non-reversible gate, but there is a reversible version of it. Maybe it acts on 3 qubits. It's a 3-qubit gate. Squeeze in some more gates in here. And so on. Oops. It's important to get the colors right. Okay, close enough. Now, starting with some arbitrary bits and applying a specific set of gates called, let's call it reversible NAND, then we can prepare here any information state. So in other words, this state will always have the form 0, 1, 1, 0, whatever. You can prepare any such state. And in other words, you can run algorithms to come up with any binary state you like. So quantum computation then contains classical computation. Moreover, for the quantum case, what we had was some generic physical process that we were simulating. And in fact, this is the origin of quantum computation. So let's write down, to appreciate this, let's write down a generic quantum state. So if it was a 5-qubit state, or an n-qubit state, then we already wrote this down. We had write down some alpha k, bk. But these are the basis elements. Now k goes from 1 to what? That's the question. What's the quantity up here? Well, if it's n qubits, if this is an n qubit quantity, then the number of basis elements, so the number of bk goes as 2 to the n. It's a large number. So in other words, this thing up here is 2 to the n. So now, if we wanted to prepare this state on a classical computer, what we would have to do is we have to store these numbers, alpha k's, on a classical computer. And the number of alpha k's there are is 2 to the n. So we have to store 2 to the n numbers. And that becomes very difficult, very inefficient. In other words, suppose you have a computer that can store 2 to the n numbers for, let's say, n equals to 50. So you have a computer that can store 2 to the n, 2 to the 50 numbers. And now I said that, okay, great, but now I need you to store 2 to the 51 numbers, n plus 1. That means you need another computer, like the one you already have, to store that one extra qubit, that one extra number, or not. There are twice as many numbers, but one extra qubit requires twice as many numbers. And this is the reason. This was noted by physicists working on quantum mechanics in computational with computational methods, that it's notoriously inefficient to study quantum mechanics using normal computers. And Richard Feynman pointed out that, well, if a classical computer is not able to deal with the size of parameters that a quantum system will have, then you may as well use a quantum system to simulate a quantum process or a quantum state. And that's the origin of quantum computation. There were a few other people who also said similar things. Feynman being famous, his words carry a lot of weight. So the whole point of quantum computing then becomes that because it's hard to simulate at the moment, we don't know how to simulate quantum systems on a classical computer. If we can devise a quantum machine where we can prepare arbitrary quantum states and simulate arbitrary quantum transformations, then already we can do a whole lot more physics than before. And there is a lot of practical value there. Turns out that if you want to work with exotic materials for, say, high temperature superconductivity or new display screens or new drugs, new solar panels, then these problems require solving solutions to quantum systems that are very complicated. And a great deal of supercomputing power is devoted to solving these quantum systems today. And a quantum computer will make that task notoriously efficient. So to put it in perspective, the quantum supremacy experiment that you might have heard about that Google did last year, they did it in a couple of days' time. Doing the same experiment on the best supercomputer would take a full year. So it's a huge advantage. Okay. So now we've combined gates and states and transformations to talk about quantum computing. So I'm not going into the details of the fundamental gates that we have. This is in the book. So we have the Hadamard gate, the Pauli gates, and we also have the control NOT gates. I want to talk about measurements. And I'm sure you've already come across the idea of measurement before. So suppose we have a quantum state So what can we measure here? Well, the measurements that you've studied so far are called projective measurements. And so projective measurements look like this. And we'll study more general measurements. And the probability of observing this quantum state in state 0 or state 1, we can write as P0. And the rule, which is often called the Born rule, is this. So the probability that we find our quantum system, our qubit in state 0, is given by this. If we expand that out, it's just alpha square. And the probability that it's in state 1 is this. And if we expand that out, it's just beta square. And this is why we require that alpha square plus beta square is equal to 1. Because we want to observe our system and we want it to be either in state 0 or state 1. We don't want the system to not have any idea. So the probability conservation is the reason why alpha square plus beta square is equal to 1. So what happens if, let's go back to the idea that suppose we write down psi as cosine theta over 2, 0 plus e to the I phi, sine theta over 2, 1, and I'm going to encode theta as some real number that includes, that is a binary representation or hexadecimal representation of complete works of Shakespeare. Can I read that out? The answer is no. Or if I have, let's say if I have many copies of psi, if I have many copies of psi, then I can do many measurements on psi and I can estimate. So in other words, every time I make a measurement, I have some probability of getting state 0 or some probability of getting state 1, which is given by alpha square and beta square. So what I do is I do many measurements, and after doing many measurements, I have a pretty good estimate. So I have a estimate for, so I'm going to write that as an estimate for P0, which is going to go like cosine square of theta over 2. And so a bunch of times I'll get value as, I'll get outcome 0. And sometimes I'll get 1. So estimate of probability of 1, I'm going to measure as sine square of theta over 2. So suppose I can do that. Then I can take the square root and I can take the inverse cosine and inverse sine and I can estimate. I get an estimate for theta and I can devise some metric so that estimate for theta minus theta goes to 0. In other words, I have a very good estimate for theta. So the point is that while you can encode the complete works of Shakespeare into a single qubit, you can't read it out in a single measurement. And that's because quantum measurements give you outcome probabilistically. So that all of the information that is encoded into theta is somehow only available at the quantum wave function level, and when we make a measurement, not all of it comes back. So the power of quantum computing isn't entirely in the fact that we can encode arbitrarily large amount of information in a single quantum state, but it does somehow tell us that we are able to put more information into a single quantum state, and perhaps we can manipulate it better. So we may not be able to get the complete works of Shakespeare out in a single measurement from a single qubit, but we might be able to manipulate it. We might be able to process it. Now, if we count the number of copies, so in other words, I say many copies. So how many copies? The number of copies that we would need in order to read the complete works of Shakespeare out is going to be approximately same as the number of classical bits we would need to store the complete works of Shakespeare. So we're not going to get a huge amount of advantage. But in some cases we might, and we'll cover those later in the year. Okay, so that covers the ideas of measurements, transformations, and states for quantum mechanics, and I've also covered a little bit of quantum computing in that. So I'll just give a 5-minute introduction to why quantum computing might be interesting. I've already motivated it quite a lot, but let's do it from a computational complexity perspective. So let's let me draw the set of problems that a classical computer can solve efficiently, probabilistically. And this set of problems is called BPP, bounded error probabilistic polynomial. So these are the problems that a classical computer can efficiently solve. Now there's this larger class of problems that a classical computer can verify but not solve. So a good example, and this class is called NP. So these are the problems that can be that can be verified but not necessarily solved. So a good problem here, a good candidate is factoring. Suppose I give you a number x and tell you that r is a prime factor of x. So I give you x and r. Well, what you can do is simply take your x can be a large number, r can be a large number. You can just divide x by r and ask whether this is in a set of integers. You can check that, and that takes a few seconds to do. But suppose I say, I give you x and I ask you find its prime factors, or find a prime factor, find r. This is very hard and we don't know how to do that. Now it turns out that a quantum computer can solve factoring efficiently. And this class is called BQP, Bounded Error Quantum Polynomial, BQP. So everything in yellow is a set of problems that a quantum computer can solve efficiently. And it includes everything a classical computer can solve efficiently. And that's because of the argument that I made earlier that a quantum computer essentially contains classical computer as a limiting case. It doesn't include everything in NP, but it does include some things in NP. So a quantum computer is thought to be more powerful than a classical computer. Now, we don't know whether factoring is in fact not solvable in a normal computer. So it could be in a classical computer. At the moment we think it's not, but it could be that classical computers can efficiently factor. No one's found an algorithm to do so, but maybe somebody will in the next few years. But there are other problems that are thought to be hard for a classical computer, namely simulating a quantum process, simulating a quantum state. This is thought to be very inefficient for a classical computer, and a quantum computer it should be able to do efficiently. So these are the reasons why people are interested in building quantum computers. There's value in on the scientific front for both computer science and physics, and as well as chemistry and material science, and there is value in terms of market share. It can solve problems that have practical importance and therefore might be able to make someone some money. Okay, with that, I'll stop for today, and we'll start with an example of a quantum algorithm that has some speed up next time.